In this video, we'll be talking about the quicksort algorithm. Now, we've seen a number of sorting algorithms so far, but all the algorithms, bubble sort, insertion sort, and selection sort, these all take n squared time in order to do the actual sorting. Which means if we have 1,000 items, it's going to take up to 1,000,000 comparisons in order to get these things sorted. Now, we can do a better job, or a faster job, of sorting these things by using the aptly named quicksort algorithm, which uses recursion and this notion of divide and conquer in order to solve the problem a little bit faster. So the steps of quicksort start by selecting a pivot. So pick a random element out of the list. Once we have our pivot selected, what we'll do is we'll compare that pivot to everything else in the list, and we'll create two sublists out of it. All the elements that are less than or equal to the pivot will go in one sublist, and all the elements that are greater than the pivot will go in the other sublist. The pivot itself will just stay on its own. Now, these two lists won't be sorted, but we'll have some information that everything small is in one list and everything big is in the other. So what we need to do next is sort those sublists. So we'll call quicksort to sort those two sublists. Okay. Now eventually, quicksort's going to break that down and break it down and break it down, make it smaller and smaller and smaller, until eventually our lists are so small that they have only 0 or 1 element in the list. At that point, those lists are sorted. And all we'll need to do then is bring everything back together. So let's see an example. Our sorting algorithm starts with an unsorted list as our input, and the quicksort says select a pivot from the list. We'll choose the first element as our pivot. Notice it's a random value compared to all the other numbers. What we do now is compare that pivot to everything else in the list and make two sublists, one where everything's smaller than the pivot and one where everything's greater than the pivot. So we have everything less than 6, the pivot itself, and then everything greater than the pivot on the other side. Now notice these two lists are not sorted, right? We have 4, 1, 5, 6. It's in no particular order, but everything in this list on the left is smaller than everything in this list on the right. So without having done any comparisons between these two values, we've sort of sorted them relative to each other. Now we just need to sort them unto themselves. So what we'll do is we'll call quicksort, and quicksort says select a random pivot. So we'll take the pivots from our list and compare everything to those, creating two new sublists. So everything less than 4 goes on one side, everything greater than 4 on the other, and similarly everything less than 7 goes on one side, everything greater on the other. And we get a situation like this, where 1 and 2 are less than 4, then we have our pivot, and then 5. Over here we chose something that wasn't so much in the middle, so everything was greater than. But notice even then we went from a list of 3 elements down to a list of 2 elements, so our list is still getting smaller with each step. Okay. One more step, so we select a pivot again, split around that pivot, and now we have a bunch of lists that have either 0 or 1 element in them. And because we were splitting them relative to pivots as we're going down, all the smaller elements move towards the left, and all the bigger elements move towards the right in this tree. So all that's left together is to stitch everything back together so we can recombine everything into one big list, essentially in the order that they're in. So, it's all well and good to explain that with a picture, but how does that translate into code? So let's create a new file here, quicksort.py, and let's define our quicksort function. So def quicksort. Now quicksort is a sorting algorithm, so its input is just a list, and needs to return a sorted list. Now quicksort, as I mentioned, is going to use recursion to solve its problem, so we're going to have some sort of base case. Now, we need a base case and a recursive case. We'll talk about the recursive case in a second. But the base case, again, is this idea that we can solve the problem without really doing any of the actual work. So the list is in such a state that we already know how to sort it. And a real good example of that is an empty list, right? If you hand me an empty list and say, sort this, I'll hand it right back to you and say, done. Similarly, with a list that has 1 element, it's already in sorted order. So we'll say list has 0 or 1 elements. So if the length of our list is less than or equal to 1, so if it's 0 or 1, you can't have a negative length list. In that case, we'll just return the list itself. It's already sorted, we don't have to do anything. Now everything else is working towards that base case. So we have this list, we need to split it apart and make our list smaller and smaller and smaller so that throughout the recursion we're moving towards that base case. So let's just type out the steps here. We're going to first select a pivot, and that's going to be done randomly. I put that in quotes because we're just selecting the first element again, but it's a random element out of the list. Once we have that pivot, we're going to split the list into 2 different lists, both above and below the pivot respectively. Okay. Now once we have these two lists, again, everything in the smaller list is going to be smaller than everything in the bigger list, but the lists themselves are not going to be sorted. So we'll need to sort both sublists. Once we have that, we have a list of everything smaller that's sorted and a list of everything bigger that's sorted, so we can just join them back together. So join everything together and return. And that's the design of the quicksort algorithm. So let's fill in this code. Select a pivot element randomly. And as I mentioned again, the input is a random list, so we're just going to take the first element and call that a random element out of our list. So pivot equals list at 0. Oops. Now we're going to need to create two sublists, so we'll call them left and right. You can call them big and small or above and below, whatever you want to call them. Here, left is going to be everything that's less than the pivot, and right is going to be everything that's greater than the pivot, in this notion that we're sorting in increasing order. Okay, so if we have our empty list, we now need to compare that pivot to everything. So we'll say for I in range. Now, the pivot is element 0, so we don't have to consider that. We can just start at element 1 and go to the rest of our list. So from 1 to the len of list. So for all the remaining elements, we want to know which list does this element belong in. So we'll ask if the list at that element is less than or equal to the pivot, then we'll say left dot append list at I. So we'll copy that element out of our input list and put it into this small list, the left one. If it's not less than or equal to, it must be greater than, so we can say else right dot append list at I. So from there, we have now two lists that are not fully sorted unto themselves, but relative to one another, everything in left is going to be smaller than everything in right. So the next step is to sort those two lists. So the idea being we're creating this quicksort algorithm that can sort any list. So all we need to do is say left equals quicksort left. Assuming that this quicksort algorithm eventually will work, which we're in the midst of making happen, this will take the left unsorted list and turn it into the left sorted list. Similarly with right, say right equals quicksort right. Okay. And now we have two lists that are sorted, and all we need to do is join everything back together. So we're going to say return if left is all of the items that are smaller than the pivot, and right is all of the items that are bigger than the pivot. We can say essentially left plus pivot plus right. So left is a list, right is a list. The issue with pivot, though, is it's just a number. So if we want to concatenate these things to join them all together, we'll have to make sure that everything is of the same type. So we'll just wrap pivot in a list here. So left plus the list that is just the pivot plus right says join all those things together, return a new copy of these items as a sorted list. So let's run this code. Let's just do it with interactive mode. So Python, it's probably a little bit small. See if I can't fix that real quick. Just make everything bigger. So python-i quicksort.py. So now we're in the Python terminal where the quicksort function exists. And let's just create a list. So we'll say L equals, and let's just take a random set of values. So 5, 8, 9, 3, 1, 5, 2, 4, 9. Sure. So there's a random set of numbers, and now we can quicksort it. So we can say quicksort L. And we can see it's in sorted order. Having duplicates didn't break anything, so we got our sorted list. Okay, so assuming everybody understood the code, which if you have questions, please stop by office hours in the Discord and we can walk through any details that are missed here. But let's move on then to understanding this algorithm. Instead of just understanding how it works, understanding how efficient it is. What's the runtime, or what's the big O notation for quicksort? Now, if we're just looking at the code, it's going to be hard to tell, right? We have this loop that goes for the entire list, so we have an idea that it's going to be O of n there, right? Because n is usually the size of our list, and it's going from 1 to the end of our list. So that might be O of n, but we also have this function call for quicksort in here. And that doesn't really show how much work quicksort's doing if the amount of work that quicksort does depends on the amount of work that quicksort does. So you'll learn in later courses how to solve functions like that, but let's instead switch back to the tree view of quicksort and see if we can't understand it there. So the idea with quicksort is at each layer, at each stage, we're splitting the list in half. In a perfect world, everything goes on, or half everything goes on one side and half of everything goes to the other side, -1 for the pivot being pulled out. Okay? So if we're comparing everything to the pivot at one stage, so we say 6 compares to all these elements, then 6 has to compare to roughly n elements, technically n-1, but again, with big O notation, we say that's approximately, or in the worst case, O of n. So roughly n comparisons per layer, but how many layers are there? Well, if we're splitting the list in half at each one of these layers, how many times can we take a list of n elements and split it in half? Well, as it turns out, this is the definition of log base 2, as we saw when we were talking about binary search in previous lectures. So log base 2 of n is a definition of how many times you can divide n by 2 before you get to the value 1, which is essentially a description of how tall this tree is. So if we're doing n comparisons at the first stage, in the second stage we're taking 2 pivots and comparing them to n over 2. So we're doing n over 2 plus n over 2, so 2 times n over 2, which is still just n. And at this stage, if it weren't such a small list, we'd have 1 pivot compared to a quarter of the items, another pivot compared to another quarter of the items. We'd have 4 pivots compared to their own quarters, so 4 times n over 4, again, roughly speaking. So at each stage, we're doing roughly n work. So if we're doing n work at each stage, and we're doing log n stages, then overall it's n times log n work. So at each stage, you do about n comparisons, but each stage the problem size gets half as big, so there's log base 2 of n stages, which means a total of n times log n, which in big O is just O of n log n comparisons. So when we're dealing with logarithms, again, we drop these small numbers because all logarithms are a constant factor of each other. Don't worry too much about that. Again, with big O, a lot of it is just talking about upper bounds or rough measures of these things. So n log n, total comparisons. So if we only have 1,000 items, if we have 1,000 items in our list, that's only going to be about 10,000 comparisons. Compare that to bubble sort, where it's n squared. If we have 1,000 items, that's 1,000 times 1,000, which is 1,000,000 comparisons. So in this case, because we're comparing the pivot to everything and splitting things in half, let's go back to the tree here for a second. We compared the 6 to everything in this list. So the 6 got compared to all these items, but the 4 never got compared to anything in that half. And this is where the time saving is, right? Everything in this list didn't compare to anything in that list, and yet we still know that everything in this side is smaller than everything on that side. Compare that to bubble sort, where we'd have to compare every pair of possible values in order to figure out what the order of every pair should be. So that's the idea behind quicksort. We can save some time by dividing these things and then sorting them individually. Now, it runs in n log n time, which is known as the best time for sorting algorithms, but notice it does so based on some randomness. Right? So if we get very unlucky with our pivot selection, so let's say for the sake of argument, the list is sorted in reverse order. So it's currently biggest to smallest, we want it smallest to biggest. Using the algorithm as we wrote it, if we're always taking the first element out of that list, then when we split the list, we're going to end up with all of the items on one side, right? If we take the pivot as the first item, that's going to be the biggest item. Compare that to all the other items. We'll have an empty list of things that are bigger than it, because it's the biggest. We'll have a full list of n-1 items for all the things that are smaller than it. And then we'll do that again. We'll take the next biggest item, and then compare that to everything, and end up with a list that has n-2 items in it. And then the next biggest item, and then -3 items. So essentially at each stage, we're only subtracting 1. So if we get very unlucky, and it is a very unlikely scenario that if we're selecting these items at random, that we'll end up in a situation where we're taking the biggest or the smallest item every single time. But if we do get that very unlikely, then since we're only shrinking by 1 at each stage, we're doing n times n amount of work, right? We have n stages, and n work at each stage makes it n squared again. So Quicksort has what's known as an expected runtime of n log n, because it's very likely that on average you're going to be splitting the list roughly in half. But there is that unlikely scenario where every so often, if you run Quicksort a million times, one or two of them might end up being pretty bad. So Quicksort's it's very efficient most of the time, but it is based on some randomness, so it has an n squared worst case time. So if we say we have 1 second per comparison, which is pretty slow, on average we expect that to take about 3 hours to compare 1,000 items, right? So it's only 10,000 comparisons. Now, if we're doing n squared time, though, that's almost 12 days, just to put that in some context. So n squared is considerably bigger than n log n time. So having a sorting algorithm that can sort in n log n instead of n squared is a very good tool to have. So I'm going to stop this video here. The next video we'll talk about a second sorting algorithm that also sorts in n log n time. Talk to you next video.